like we should set up like yeah, we should. I will.
Okay. So I just your homework was due this morning, but I just want to talk about one thing here in terms of surface area. So suppose I've got my function is f(x) equals x squared, or y equals x squared from 0 to 2, and I want to rotate that about the x-axis. So when I do that, I'll get something that looks like this. So we'll have some kind of surface like this, like the lateral surface of a Hershey's Kiss, right? Turned up on its side. So, so I've rotated about the x-axis, and suppose I'm going to let x be my independent variable. So what is my rate of change, or surface area accumulation function here? It's going to be, yeah, Nick?
It should be the integral from a to x of 2 pi f of x.
So 2 pi r.
Or 2 pi r ds.
ds, and the ds is square root
1 plus it should be dt at the end of f of prime of t.
Okay, and so what I want to talk about is r. What I want to talk about is the radius. So that radius, so you have to make really to get this right, you have to make a sketch of the surface, and you have to at least imagine or sketch the ribbons, okay, the ribbons. So if I rotate it about the x-axis, then there's one of two things about those ribbons. They're either kind of standing up vertically like this. So there's my beveled edge there, right, my slanted edge. Or they're like kind of like laying horizontally like this. So which is it? How are my ribbons accumulating to accumulate surface area? Are they accumulating this way? I know that Nick knows. Or are they accumulating this way? The first one, right? So because I rotated around the x-axis, so draw a couple, right? Draw a couple. It's really important to get this radius right. So like you could do, right, and then it's all based on what, a little tangent line to the surface, or the ds, right? Like that. There's that one there, and then for later on, for say this delta x interval down here, say it's this one. This. So those are what my ribbons are going to look like. So they're going to, as x increases through delta x intervals, those ribbons are going to grow according to ds, right? And they're going to, the circumference 2 pi r is going to sweep out the surface of the Hershey's Kiss, right? So therefore, these ribbons, getting a good image, drawing these images, is what's important for finding r, because the radius is the radius of the ribbons. So what is my radius for these ribbons? Is it x, y, a big change in x, or a big change in y? We always ask that. Is it an x coordinate, y coordinate, big change in x, big change in y? Y coordinate. It's the y coordinate. It's the distance from the x-axis up to our curve. That's the y coordinate. So this radius is the y coordinate, but my independent variable is x, so I got to write it in terms of x. So r is equal to f of x, or x squared, right? So x, and so that would be x squared, but then we need it to make it t squared for the integral. But the key here is, in this particular example, is seeing that that r comes from the radius of my ribbons, or frustums, parts of cones, and that radius is the y coordinate, and so that's x squared, and then it becomes t squared. Now I'm going to do the same exact Hershey's Kiss, same thing. I'm going to rotate it around the x-axis, but now I'm going to let y vary through delta y intervals for this example. Okay? So I'm going to let y vary through delta y intervals, but it's the same surface rotated around the x-axis. So the question is, are my ribbons vertical like this still, or now are they horizontal ribbons? So they're horizontal ribbons. Are they like this? So is that right? Is that going to get me the... No, right? That's not it. That's a different surface. That's if that function was rotated about the y-axis. So even though I'm rotating, or sorry, even though y is varying through y intervals now, my ds's are still the same. They're these little tangent lines, tangent segments to the arc, and I'm still rotating this thing about the x-axis. So my ribbons are still these. So now, integral from a to y of 2 pi r square root of now. So now, okay, so the thing that changes here is the fact that if y is varying through y intervals, now we need x as a function of y. So what is that? That's the inverse function of f, right? So that's, if we were writing x as a function of y, and what function is that? Square root of y. So if y equals x squared, then x equals the square root of y. So that's what this is as a function of y. So that's what I need here. I need now g prime squared. And now the question is, what do I put there for the radius? So again, we ask, is the radius an x coordinate, a y coordinate, a big change in x, a big change in y? It's still the y coordinate. And what's my independent variable? Y. So I need to write that y in terms of y. It's already in terms of y. So we're done. So here, the y coordinate, we need to make it x squared or t squared, because we need to write the y, the radius is y, we need to write it as a function of x, which is x squared. But here, it's still y, the radius, because it's the same ribbons, but we need to write it in terms of y. It's already in terms of y, it's y, so we're just going to put in there just t. So I guess, so when I was helping students with this homework, hardly anyone was drawing the pictures, especially of the ribbons. And the ribbon is what is crucial because it determines what you're going to put in for r. It's the radius of the ribbon. So you got to draw those. You got to draw do your best to draw the surface, and then based on your rotation, what are the ribbons? Because the radius of those ribbons it's the radius that you need in the surface area function. Does it make sense? Okay. And so in terms of the online homework, I know that there's a lot of bugs that we're fixing, and I know that's frustrating for you. It's frustrating for us as well. So rather than try to give back individual points to individual students for unfair loss of credit, what I'll do is just at the end of the semester, I'll just give a adjustment for everybody, okay, a technology adjustment. So I'll compensate you for this, for like little points here and there that you're losing because of the bugs, okay? So we'll make that up to you at the end, and we'll just keep pressing forward. And so if you're really confident about an answer and you think that there's another bug, that you guys have been speaking up, and that's good. Keep doing that, okay? So we'll get them fixed.
Question.
Yeah, please.
Can you help me understand why radius is y instead of y there? I thought you split the y instead of y.
But the radius is the y coordinate. root y is x. Root y is equal to x. But the radius is the y coordinate, right? It's all, so for both these, the radius is y. So when we're using x as the independent variable, then we have to write that y in terms of x. So it's x squared or t squared. But when we're writing the independent variable in terms of y, it's still the y coordinate is the radius, but in terms of y, that's just y. So it doesn't change. So we use t. Now what changes here is this. So this one is what? Function of x, the derivative as a function of x squared, but now here we use the inverse, the g prime here, because now we're in terms of y. Okay, other questions? All right, so we've done kind of a whole geometry unit here, right? We worked on accumulation of signed area, accumulation of volume, accumulation of arc length, and now surface area. So that we've been dealing with a lot of geometry, ways of using integral to do geometry accumulation functions. And so now we're going to kind of transition or change gears to more like science and physics applications. So in the first class, they groaned. You guys were a little quiet. I heard a yeah. Oh, yay, okay. All right. So let's start with quantities of motion. Quantities of motion. So probably very few of you were alive when when NASA had the space shuttle program. So they flew these in like the 80s, maybe the 90s, I'm not sure. But this is the space shuttle. And so it was this gigantic plane that they launched like a rocket, and it went into space, and it did all its cool space stuff. You know, went to the space station, and it orbited, and then when it came down, it landed like a plane. This gigantic thing that landed on a runway like a plane. Landed near Florida. I think Florida is where it landed. One of them didn't do so great on the way up. Okay, you probably have seen that. Okay. But they've discontinued this program. But anyway, this makes a good example. So upon takeoff, this is about right that the velocity, these are the velocities every second after takeoff. 30 meters per second, then 60, then 90, then 120 meters per second. And so the question is, what do you notice about velocity in terms of topics we've been talking about in this course? What do you notice about velocity in the first 4 seconds or so? Yeah. Okay, so in terms of the velocity, is it constant velocity? So what's constant in terms of the velocity? Rate of change, right? So the rate of change is constant because every second it's doing what? Going up by 30. Okay? So we say that it's going up 30 meters per second every second. So now, based on what we've learned in this class, can we explain that in a meaningful way, right? So yes, every second the speed goes up 30, but do we know more than that? Is there a broader meaning for that? We've talked about it. Do you remember? All right, so this is a constant rate of change, and we've worked periodically on and off on a broader, fuller meaning for what a constant rate of change is. Mark thinks he knows. Tell me your name in the back. What's your name? Justin? What do you think? Okay, so it has to do with that, right? So we said we were going to frame what equals mdx? dy, right? dy, yeah, dy. So we said this is going to frame our meaning for constant rate of change. So how can we then explain the 30 using our meaning for constant rate of change? What do we say? Or how do we explain that? Do you remember? So someone else had their hand up. Was that Mark had his hand up?
I was going to say
Okay, yep. That was kind of, yep, that was what we learned, all right? And so then we specifically looked at constant rate of change, and we said, yes, sir?
What is the change in x?
Yeah?
dy changes by 50 times x.
Okay, so excellent. So let's say, what is a change in x here, in this case? Every change in seconds, given a change in seconds, we say the change in velocity, right? So given a change in any change in time, the change in velocity is 30 times that change in time. So, for example, what's the change in velocity for a change in time of half a second? 15, right? And what's the change in velocity over 2 seconds? 60, right? So the point is that we know a lot more than just how much the speed goes up in 1 second. We know how much the speed goes up in any change in seconds, right? If it stays at a constant increase of speed, right? So, and we get that by multiplying 30 times the change in time that we pick. That gives us the change in speed. Okay, so now I want to use that. So that's the last thing. Okay, so when I use this fact to say what the speed would be at 4.7. Okay? So, and I want to use this fact too, that at 4, it's 120. So don't make dt 4.7. That's my only restriction. Don't make dt 4.7. Use the fact that at 4 seconds, the speed is 120, and then use dv equals 30 dt to calculate what the speed would be at 4.7 seconds. And then you can confer and collaborate as you do that. But my only restriction is don't say that dt is 4.7 seconds. It's too big. It's too big of a dt, okay? Okay. So I heard some good work up here. So in the red and white, sure, right here. Tell me your name. Yeah, good. I'm sorry, behind her. Jess, sorry. Juliana, you're next, okay? All right. Jess, did you guys figure this out?
Yes.
Tell me.
So it would be dv is equal to 30, and then in parentheses 4.7 minus 4.
Okay, which is, so your dt is?
Yeah, the dt is 4.7 minus 4. And then if you're looking for like the total accumulated like based off of the 4 seconds,
Okay.
120, then you add.
Right, so the 30 times, so if you pick a dt of 0.7, like this would be the dt, then you get what? What does that give? 21. And what does the 21 mean? 21 is? dv, right? Yep, so take 30 times the change of 0.7, you get a change in speed of 21, and then what do? Yeah, so that's the change since 4, so then we're going to add it to 120. So we're going to do 120 plus 30 times 0.7, and we get 141. Look familiar? Look like anything we've done? What is that like? Total, some more people are saying it. So if you're thinking total or saying total accumulation, that's right. It's all the accumulated. Okay, so it's a little strange to think about accumulating velocity. So rather we'll think about, which makes sense, is think about accumulating changes in velocity. That should make perfect sense. That as the velocity is changing, you can accumulate those changes. And so this is all the accumulated change in velocity in the first 4 seconds. So it's like all the previously accumulated changes in velocity, plus the next little change gives us the new total velocity, or the new velocity. So yeah, so that mirrors our total accumulation function, just like we've had before, and we've had what the net accumulation function as an integral here. That's kind of doing the same thing. It's accumulating all the changes since our starting point. We used 4 as the starting point here. Okay. Any questions on that so far? Okay, so this is what we say. We can say changes in velocity are accumulating by 30 meters per second each second. And what's the rate of, this is the rate of change of velocity. And a few of you were saying we have another term for that. What is the rate of change of velocity? Acceleration, right? Acceleration. So we can say the acceleration of the shuttle is 30 meters per second per second. Okay, so what does that acceleration function look like? So here's, I want to graph the acceleration function, or the rate of change of velocity for this situation. Seconds on the horizontal axis, feet per second on the vertical axis. What will that look like? Draw it with your finger. Like this? No, like this, right? So it's acceleration, which is constant. So it's just staying constant at every point in time. The acceleration is 30. And the meaning of this constant rate, so we've already said that. Meaning of the constant rate is given anybody? Good, right? Yeah, and I excellent, right? So given any change in time, the change in velocity is 30 times that change in time. I don't recommend lumping the seconds together and doing second squared. I know that's very, very common, but it takes away from the meaning that this is how much the velocity is changing every second, okay? And then we know that we can find out how much it's changing in any amount of time, okay? But lumping the second squared together, I think it kind of robs the meaning here of what acceleration is. Okay, so we know that dv equals 30 dt. Can we also say that the velocity equals 30 times the time? Is that true? Or not? Why is that true? There's a reason that's true. That's not always safe. You can't always do that. Yeah. But then you could have a constant. Yes. Because it starts at 0 meters per second. Right. So when t equals 0, v equals 0. And so you can think of these changes as since 0. And because of that, we can also say that v equals 30t. But that you can't always do that, right? So if you have constant rate of change, this is always true, but this is not always true. But it's true in this case because at time equals 0, the starting speed is 0. So I'm going to call this function g. And so we got a velocity function is 30 times t, or v is 30t. So now you have a little task here. So I want you to write this function an alternate way. So g of t could also be expressed another way, the velocity, in a way that represents velocity as the net accumulation of tiny changes in velocity. Okay, so here's 2 hints. The first hint is the way you're going to write this function is as the net accumulation of tiny changes in velocity. The second hint is we've been doing this all semester. Okay, go. So hopefully we all can do this. So we're going to rewrite this function g of t that we know is 30t, but now this time as the net accumulation of tiny changes in velocity. Similar to what we've been doing all semester. Please know this. Please know this. So Juliana, I promised, you're up.
Okay, so G of t equals the integral from
Yep.
a to x,
So let's use t because I'm using the independent variable as t, okay?
a to t of 30x dx.
30. So x is also usually like the independent variable, so let's just pick something entirely new. So how about u? So you said 30u du. Okay. What do we think? A couple of people raising their hands. Agree with that? Really close. Someone in the back. Yes, sir. In the blue shirt. Yep. He just wants 30 du. So what is this about? So how do we choose what we're going to integrate? What is that? What is it that we integrate? Rate of change. The rate of change of whatever this is. So is 30u the rate of change of velocity? So what should it be, Juliana?
30.
Just 30. Just 30. That's our rate of change. So if you said, and so like I didn't use for when I first wrote this g of t, I didn't use the two argument version. So this should really be, if I'm not going to use the two argument version, then I'm going to start from 0. But if I use the two argument version, then it will be integral from a to t. 30 du. Or you could write a of u, right? So if you wrote a of u du, that's fine too, because a of u is 30. Is there a question? Yeah.
How do we decide when to use one argument versus two arguments?
Oh, we're all getting two arguments from here on out. Yeah, so that's the goal. Always use two argument. But it was just a little bit too much of a giveaway for me to do the two argument thing. So I wanted to make sure you knew it was integral without it. But yeah, let's do two argument from here on out. Okay, so we've got the same function, 30t. One version is 30t. The other version is integral from a to t 30 du. Or this one, okay? So they're the same function, but in totally different forms. So this form is called open form. What do we mean by open form? Open form, it reflects the meaning of where these velocity values are coming from. So it reflects this process. Notice this was the result of the whole first week of class. You know how fast something is changing at every moment. You want to know how much you had. So first we got small changes in velocity, which would be m dx, or in this case, 30 du. So 30 du is a small variation in velocity. And then we're going to add those all up, starting from 0 up to t, to get the total accumulation of changes in velocity. So this notation, it kind of encapsulates the whole first week in class, the stuff that we worked on, to come up with this accumulation function. Okay? So that's the good thing about it, that when you look at it, you see the process, you see the meaning, okay? But the downside is that it doesn't readily or easily compute values of velocity for us, right? So all semester long, to get values of this function, what did we have to do? GC, right? We'd have to define the function as an integral function and then use function notation and let GC do the work, okay? So it doesn't readily give us values of the dependent variable, in this case velocity. So that's open form. So it reflects the process, it reflects the meaning, but it doesn't spit out values easily, right? We need technology to do it. On the other hand, this one is called closed form. Closed form often does not reflect any meaning at all, right? So it's made up of all the functions you're familiar with in your whole math career. Polynomials, sine functions, exponential functions, logarithmic functions. So all the familiar functions, and those in any combination. So it's arithmetic, familiar functions, but it doesn't reflect the meaning the way this does. But what's the advantage to that? That open form couldn't do. Right? Can generate values of velocity really easily, even in our head. Like, right, we could just do it in our head. So like for easy functions like that. So, if the time is 5, we know its velocity is 150. If the time is 1.5, velocity is 45, etc. So closed form is based on familiar functions, and it can rapidly and easily generate values of the dependent variable, right? It just cranks out values for us. Sometimes even if it's easy enough in our head, we can do it in our head. Okay? So, like I said, all semester we've been setting up open form net accumulation functions, and then in a week or so we're going to spend a whole unit on learning techniques to starting with open form accumulation functions, learning to write them in closed form, so that we have this form that helps us generate values of the dependent variable fast and easily. Both are very good, and so we want both, right? So we've been working hard on this, and then we're going to start learning all these different techniques for getting the closed form net accumulation functions. Make sense? Okay, let's look at a new example. Any questions? All right, so I got 2 cars, and these are their acceleration functions. So A1, car 1, is that acceleration function there? 0.7t plus sine 3 pi t over 5. And then of car 2, 3 minus 3 cosine 2 pi t over 15. Okay, are these functions expressed in open form or closed form? Closed form, right? These are closed form functions. And so I want to ask you questions here. So these are the acceleration. Those are those functions graphed. Car 1 is blue, car 2 is red. Couple questions. Which car is moving faster at 2.5 seconds? Which is right here. 2.5. And when do you estimate the cars would have the same speed for the first time by looking at the graph? So you're not doing any calculations here. You're just, by observing the graph, answering these questions. Which car is moving faster at 2.5 seconds? When will the cars about have the same speed for the first time? Take about a minute. Talk to each other. Go. Question? Yeah. I'm sorry? Oh, just do it based on the graph. But just do it based on the graph. Okay, what do you think? At 2.5 seconds, which car is going faster? What do you think? Yeah.
Car 1.
Why car 1?
It has a greater acceleration almost the whole time.
Right. So yeah. So as a much greater acceleration. So you think about the accumulated changes in velocity are going to be much greater than the accumulated changes in velocity for car 2. Now, starting around 2 seconds, it reverses, right? So now car 2 is accumulating more higher change in velocity than car 1 is. Why do you think that car 1 is still going faster after 2.5 seconds? Yeah.
The area under the curve, the blue curve is greater than the area under the red curve, which is the velocity.
Yeah, okay, that's true. But I really want to take our focus off of area and think more about how you would think about accumulated changes. So I've been on a mission to try to change your thinking that integrals are always about area, right? So they can be about area. We can use integrals to accumulate area, signed area, but we can also use it to accumulate volume and arc length and what surface area, and any quantity, right? So we can do a net accumulation of any quantity. Okay, so yes, the accumulated changes in velocity of car 2 here are greater, but not enough to make up for the damage done by car 1 here, right? You can see that those accumulated changes in speed are much greater for car 1 in the first 2-ish seconds than that last half second. Okay, predictions for when the cars will have the same. So what about right here? Which car do you think is going faster at about 3.5 seconds? Still car 1, right? All right, now definitely car 1, right? Because now if car 1's going faster here, that's going even faster here. So when do you think they might have the same speed for the first time? Just ballpark. Someone said 7. 6. Yeah, somewhere in here, right? Somewhere in here. 5-ish to 7-ish is car 2 is really gaining speed here a lot faster than car 1 is. So somewhere in the 5 to 7 range, we think. How can we know for sure? So how can we find out for sure that the exact time, say pinpoint it, when car 2's speed catches up to car 1's speed? What could we do? Okay. So and then what? So we could write a speed function for both. So let's do that. So what would this? I'm going to call the speed of car 1 v sub 1. A comma t. How do I write this function? Yes, sir. Very good. So we want to use something different than t now. T is our independent variable, so we got to use something different. And the rate of change of speed of car 1 is the acceleration of car 1, or a1 nu. Is this what you to have it right? Okay, and then I can do the same thing for car 2. And how about these, the velocity functions? Open form expressions or closed form? These are open, so they don't lend themselves to doing algebra or cranking out values. So, can we set them equal and solve for t? No, right? Because the integral is just showing process. There's no algebra and solving for t that we could really do there easily at this point in the game. So we need a different way to figure out when those speeds are going to be the same. Any ideas? So now I'm gonna graph those over here on the right pane. Have we talked about using apostrophe or a quote? That opens up the right-hand window pane. Doesn't mean derivative. So how can I find out when their velocities are the same? Yeah, right? So the graph is like so super helpful here. When trying to set those integrals equal and solve for t is like near impossible, or we have no tools for that, to do that, just graph them both and look at the intersection point. And so was our prediction correct? Somewhere around there. So what is it? 5.6 seconds about 5.6 seconds. As we said, somewhere like 5 to 7-ish, somewhere is where the cars will have the same speed for the first time. Okay, what about, so at that 5.6 seconds, are they in the same place or is one car ahead? Are they in the same place or is one car ahead at the 5.6 seconds. So here, so car 2 is behind, and now car 2 is caught up to car 1, so it's passing car 1. Is that right? Tell me.
It's just the velocity, the speed of the car.
Okay, so who's ahead then?
They just have the same speed.
Right?
Yeah. But
So
the
can
blue car should be ahead.
so he's saying car 1 is ahead. Agree with that? Yeah, because it's accumulating distance, right? Velocity is the rate of change of distance, and so the first car is accumulating distance at a greater rate than the second car. So by the time the second car matches its speed, it's still way behind, right? So it's still way behind because it hasn't accumulated as much distance as this first car has at a higher rate. So will car 2, so then what happens after that? So car 2 speed is greater than car 1 speed after that. So will car 2 catch up to car 1 in the first 8 seconds? I'm showing it up to 8 seconds. Will car 2 catch up or not? How many say yes? How many say no? How many abstain? As many of you are abstaining. You don't have to abstain. You know? So, do you think it's going to catch up or not? How can we find out? I want to find out if car 2 catches up to car 1. Is it going to pass it before or at 8 seconds? Will it pass car 2 past car 1? What can I do? Yeah. What's that? Arc length? Okay, so is the distance the car has gone the same as the distance along the velocity curve? So that would be if that were true. So it's not. Yeah. Yeah, go ahead. Right back. No, not area. So, yeah, I'm trying to get. I know they've told you it's all about area, right? But this is about, we're talking about velocity and distance and time. So, yeah.
We could integrate the velocity functions, get a position function.
Right. So we're talking about distance. And what's the rate of change of distance? Velocity is the rate of change of distance. So we're going to do the same thing again. So now we're going to set up position functions. And I've got that kind of already here. So in one pane here, I've written the acceleration functions in open or closed form? Closed. Velocity in open form. And now position in open form based on speed in open form or velocity in open form. So this is like 2 layers of open form, okay? Speed is in open form, position in open form based on velocity written in open form, okay? Over here, I have the same position functions, open or closed form. Complicated, but still closed. Still, it's t cubed, sine, and t. This one, t squared, cosine, and a constant. These are still closed form. They're kind of longer and uglier, but they're still closed form. So it's the same position functions of the cars and closed form versus open form. Okay, so now watch. I'm going to graph the open form version of these position functions, and look what happens. What's going on? Why is it taking so long? Yeah, because every position is based on accumulation of a bunch of changes in position based on velocities. Each one of those velocities is an accumulation of changes in velocity based on acceleration. So it's like this double layer of open form is why that's taking so long. Do it again. But over here, look at this. Okay, and now I'm going to graph those same functions that were given in closed form. Okay, keep your eyes open. Don't blink. Ready? Watch. Ready? The other one's not turned on. What happened? Oh, I forgot to do the T. Try it again. Ready? Wait, you want to see it again? Wait. Watch. Don't miss it. Okay, why the huge monumental difference in how these graph? The ones in open form took like a minute to graph. Ones in closed form, instantaneous. What's going on? Yeah. Yes, the computer has to do a lot more work to solve these open form, use a numerical method to solve these open form functions, especially when they're layered on top of each other, right? Position is open form of velocity, velocity open form of acceleration. But with a closed form is, the whole point is fast results, easy computation, so the computer can do it almost like instantly, whereas the open form takes a long time. So, what was the result? Did car 2 catch up or not? No. Almost. By 8 seconds, so close, but didn't make it. The exciting conclusion. Okay.